its place in the energy transition. I'm David Ball, the Chairman of the Power Industry Division Northwest Centre, and I'd like to welcome you all to this lecture. It's been organised by the PID Northwest Centre and it's shared with the Greater Manchester area of the IMechE. The duration of the lecture will be about 40 minutes, followed by about 15 minutes of questions. If you have questions, will you please put them in the question and answer box, and Kusum Trika will field them after the lecture. Will you all please switch off your microphones and cameras during the lecture? This lecture will introduce carbon capture and its potential role in industrial decarbonisation. PMW have developed an advanced cryogenic process, low environmental impact with low energy consumption. It will review the technology, highlighting the challenges and how they're addressing them, together with describing some potential applications. Our speaker is Paul Willson, the Managing Director and Founder of PMW Technology Ltd. He's had an extensive career in the development of new technologies. Paul has been in senior roles in major consultancy companies with a wide experience of energy efficiency and decarbonisation projects. He has contributed to the government's earlier carbon capture projects. Ladies and gentlemen, your speaker for today, Paul Willson. Over to you, Paul.
Thank you very much indeed, David. I will share my screen, all being well.
Yes.
And we begin. There we go.
I can switch my camera off.
Right, well, good evening, everybody. Thank you for joining us. PMW is a small company. We've been, as David said, we've been in the business for 5 years or so, since we invented and patented our carbon capture technology. Of course, in the nature of things, we learn a lot about the competition and the state of the business of carbon capture. So, to introduce carbon and capture, firstly, why do we do it? Why do we consider it worth doing? The carbon emissions, as are well understood, have a severe climate impact that the United Nations is very keen, everyone is very keen, I think, to minimize the effect without too many adverse effects on humanity. Many industrial processes have unavoidable carbon emissions. There are carbon emissions we can avoid by substituting fuels for fossil fuels, for example. But many processes, glass, ceramics, even oil refining, has unavoidable carbon emissions associated with the process themselves. And importantly, whatever we do, we are presently burning a large amount of fossil fuels, and we can't suddenly switch them off, much as one would like to. We can't switch them off overnight and move on to a green economy. We have to have a transition path so that we can move from one to the other without disruption to human life that's excessive. Carbon dioxide is a problem. Where we are actually capturing carbon dioxide, whether it's from treatment of fuels before they're burnt or from capture from combustion products, they need to be disposed of. Geological sequestration is the grand term for putting it in the ground and burying it. There are different processes here. The most established one is to inject it into a saline aquifer. The Sleipner field in the North Sea has been used in that way for over 10 years now, successfully injecting large quantities of carbon dioxide safely under the sea. That was not capturing from exhaust gases, but from treatment of natural gas. But you can do the same into salt caverns or depleted oil or gas reservoirs. And in the reverse process of fracking, you can put carbon dioxide into coal beds. I think there are different issues associated with these alternative technologies, but the security of storage in many of them is no longer debated. There are technical challenges in reliably delivering carbon dioxide back into geological structures, but they're not otherwise a problem. The other alternatives include mineralization, where carbon dioxide can be reacted typically with a rock of some form to produce, for example, magnesium carbonate, dolomite, a mineral that you can then use in the construction industry. That's a permanent disposal. There's a finite amount of capacity for this, but a large amount of rock that would mean we could do a great deal more. Then the other alternative is the CCUS bit, the reuse. The little diagram below shows one possible reuse, which is to contribute to the production of polyols that are preliminary elements of polyurethanes in carbon reuse. That is a useful process. We can also go one further, and that is create a methanol cycle where carbon dioxide is recycled using green hydrogen to produce methanol. Methanol is a relatively civilized fuel that can be burnt in engines on board ship, and you can capture the exhaust gases from the engines at a high percentage efficiency, particularly with our process, and bring the carbon dioxide back as a circle. So we have a cyclic treatment of carbon dioxide and methanol, using that to carry hydrogen energy on board ship. Actually, putting the hydrogen on board the ship itself is far from straightforward, because liquid hydrogen exists only at 20 degrees Kelvin. That is extraordinarily cold, and consumes considerable energy to be converted to the liquid form, and to carry enough liquid hydrogen to do a substantial deep ocean voyage is not really feasible at the present. To look at the processes that we use for carbon capture, the most established is the Amine process. This has been used in chemical engineering for many years for removing carbon dioxide from the production of ammonia, for example, where you create hydrogen from natural gas. The Amine process uses a chemical, an amine, which is an organic ammonia form, to chemically absorb the carbon dioxide in a solution. You use quite a large vessel and you wash the carbon dioxide out of the gas stream in a tall column, typically 15 to 20 meters tall. The solution of carbon dioxide then has to be heated to regenerate the solution for reuse and to recover the carbon dioxide. This is a very substantial amount of energy required to do this, and there's a lot of work been done to reduce that energy consumption, which has borne some fruits, but it's still an energy intensive process. The chemical solutions are unfortunately also toxic. They're not the kind of thing you want to spill in the environment, and you need to handle them carefully as a human operator. And the solution is damaged by exhaust gas trace pollutants, such as the sulfur oxides and nitrogen oxides. So the solution needs to be regenerated or replaced progressively as it becomes exhausted. The good thing about the Amine process is that it's relatively easy to scale up. It's not unlike, in some respects, the FGD processes for sulfur removal downstream of a coal plant. So it is something that can be done at a very large scale. Membrane processes are an alternative. These have been used again in treatment of natural gas flows with high carbon dioxide contents. They use a selective membrane that is porous to carbon dioxide, but much less so to the the hydrocarbon molecules. And the same thing can be done with exhaust gases. However, it requires significant pressure differences to drive the separation, and the selectivity isn't perfect. So there is always going to be combustion gases coming off with the carbon dioxide and carbon dioxide left behind after the separation. So this means that multiple stages of separation are required, typically 3 or more, to get an adequate purity of carbon dioxide and an acceptable reduction in carbon dioxide content of the exhaust gases. And of course, as soon as you have multiple compressors, you have energy intensiveness. And the membranes, as we can see with these stacked modules, have limited permeability, so that you require a large number of elements to successfully treat the gas. And over a period of time, typically 5 years, the membrane performance degrades and needs to be replaced. And the membranes are the expensive part of the process. So this is not a great financial incentive. There are cryogenic processes. Ours is a cryogenic process. It's a little different from the current ones. These separate carbon dioxide by freezing the carbon dioxide in a so-called desublimation step. What this means is that the carbon dioxide, well, the gases as a whole, are cold enough that the carbon dioxide deposits as a frost. Carbon dioxide doesn't condense like water does to a liquid. It goes directly from vapor to solid. So inside our bright stainless vessels on the right, we have heat exchangers onto which the carbon dioxide freezes, just like the inside of your domestic refrigerator. And then once the fur has built up too much, you switch them off from absorbing and warming relative to -80 perhaps, to melt the carbon dioxide off the surface again. So, or by warming it to the appropriate temperature to a gas. However, just as the domestic refrigerator suffers from the furring up, these also suffer from furring up, and the heat transfer degrades, so you need a larger heat exchange area than you might have thought. And then while you're freezing one, you've got to thaw another, and you've probably got a third one in transition. So you end up with multiple large heat exchangers, which makes it expensive and makes challenging scale up for this technology. It's used particularly for treatment of biogas, where the carbon dioxide concentration is up to 50%, but the value of the product of the biogas stream or the biomethane stream is worthwhile. Then we have the more extreme form of carbon capture, direct air capture, where we actually wash carbon dioxide out of the air. And this is much more challenging. Typical exhaust gases, even from a big gas turbine, are of the order of 4% carbon dioxide in the exhaust gas. In the atmosphere, it's 2 orders of magnitude smaller, 0.04%. So the amount of gas we have to process to extract significant amounts of carbon dioxide is enormous, and the necessary chemistry needs to be fierce to take the carbon dioxide out of such a low concentration medium. So the processes you see on the right by carbon engineering, for example, use a strong alkaline solution to dissolve the to absorb the carbon dioxide out of the air. And then that the potassium carbonate solution that's produced is regenerated back to potassium hydroxide using quicklime, and then the quicklime is in turn, the lime is in turn calcined to recover CO2 and regenerate the quicklime, all of which requires energy. And this process in particular uses a substantial amount of heat, so that about 1/3 of the carbon dioxide that's sent to storage is in fact from the fuel, not from the atmosphere. So we see very large volumes of air to be processed, a large process plant in the middle there representing this example, a large heat demand to recover the CO2, and challenging integration with renewable energy sources. It's quite difficult to just substitute renewable hydrogen or renewable electricity into this process. Now, the government has been working for some time on industrial carbon capture clusters, where areas of the country are linked together so that power plant and industrial processes capture carbon dioxide locally and dispatch it through shared facilities to sequestration in the North Sea, or Irish Sea, in fact, in this case. They've started the program now, and they've committed to 2 industrial clusters by 2025 and 4 by 2030. The first tranche, the first 2, are selected to be the Northeast cluster, that's Humberside and Teesside, and the Merseyside structure run by Cadent, the HyNet project. And the Acorn project, which reuses pipelines and oil and gas facilities offshore northern Scotland, is the reserve project and may form one of the later extensions of this project. For each of the projects in Merseyside and in the Northeast, individual capture projects from process plant are being negotiated. 8 of them are currently under negotiation, and a large one with Drax is in discussion, but not at the final stages. And there are 2 big hydrogen projects that will create hydrogen from natural gas, send the carbon dioxide for sequestration, and distribute the hydrogen for industrial applications particularly. There will be some trials for injection of hydrogen into the national gas grid for domestic use. The scale at the present time is relatively limited. These 2 clusters will probably address initially only 5% of UK industrial emissions. So this is quite a small part of the overall UK scheme. Now, the carbon emissions from the country are largely recorded and regulated by the EU Emissions Trading Scheme, EU ETS, and that has a big database that reaches back to the 2010s, and those data elements explain how the individual industries are emitting, what the individual sites are doing. Because they have a certain amount of commercial significance, the information is quite out of date. But I've analysed the latest data sets, which is about 5 years old, to illustrate the different characters of the industries and their emissions. So looking at the overall figures, the cumulative emissions, as you look at ranges of size, these all double progressively from 100 tonnes per year up to 1 million tonnes per year and beyond. You can see that the largest tranche, which is primarily big steel works and big power stations, represents the largest single step, that the contribution of the smaller sites is relatively modest. However, when you look at the number of emitters, there are very few large emitters and a deal more in the middle range that emit around 10,000 tonnes a year, which are your typical local industry, if you will. So where do you start with carbon capture? You can certainly go for your big targets, but is that the way to go when you've got technology that none of the technologies yet are proven? You wouldn't necessarily start doing Drax with your new carbon capture technology. You probably want to start somewhere smaller and work up. So where do you begin? Power generation has a weird footprint because you have the power stations proper, which are the peak on the right hand side. The numbers of them is quite small. And then on the left, we have the dozens of small peaking power stations that have been built recently to balance the electricity network. And at the lower end, we probably got some plants that have hardly been used because their costs are too high. So very small emissions down there. The chemical sector is a more balanced group with small specialist chemicals at the left-hand end and big chemical operators producing plastics and whatever on the right-hand end. So the BPs of this world are on the right, and the specialist chemicals for skincare or pharmaceuticals are on the left. Energy systems for heating, the contracted, often CHP schemes providing heat and power for commercial and hospital sites. There's obviously a good cluster here. Again, around the 6,000 tonnes per year, there's quite a group, quite a tightly packed group, but quite a large number of installations of that technology. An extreme at the other end is data centers. These are often backup diesel sets for data centers, but they also have, there are one or two that run pretty much base load, supplying electricity to banks or internet service centers. Looking elsewhere, shipping has a similar footprint, that the range of ships that we see, the different types have different footprints according to their speeds. But again, 30,000 tonnes per year looks a pretty central figure for many of the ship types, and very few exceed 250,000 tonnes per year emissions from their engines. So our process, I can get to this now. Our process, we call it advanced cryogenic carbon capture. It's aimed at cleaning up exhaust gases. It's not claimed for other purposes. It's a low temperature process, uses the physical separation, frosting process to remove carbon dioxide. We use a patented moving bed technology. So the overall process includes a quenching stage to bring the temperature of exhaust gases down to a reasonable level, then a cooling stage that brings the gases down to perhaps -100, followed by the separation where carbon dioxide is frosted out, all supported by a refrigeration system, and we produce carbon dioxide as our separated products. So the principle here is that carbon dioxide vapor pressure, as you go down in temperature, the vapor pressure, you'll start to deposit carbon dioxide at about 170 Kelvin, -100 degrees, at 10% carbon dioxide in your exhaust gases. To reduce that by 95%, we only have to reduce the temperature by a further 23 degrees, which is really not a huge amount. You've already done 100 degrees of work. To do another 23 is not so bad. So our process starts with a quenching process. These are very conventional. They're used on board ships. They're used for cleanup of exhaust gases. They use either a circulated stream of water or a once-through process according to the application and scale. We apply an additional cooling to our quenching process to bring the temperature down to near freezing point, to reduce the water vapor content when we go below freezing point, to make it easier to handle. And this process washes out a large part of the particulates. It takes out the soluble sulfur oxides and reduces the nitrogen oxide content, particularly the nitrogen dioxide that dissolves below about 20 degrees in water. The separation step has two parts. The first step is our cooling stage. Now we use a high performance moving bed heat exchange. Now moving bed heat exchangers are not so common, but they are an item of commerce where you use a granular material, typically of the order of millimeter, to slowly move with the gases flowing in the opposite direction. You get intensive heat transfer, and it allows you to use the bed to carry the cold or heat from one section, one gas stream to another. So in our heat exchanger, the temperature goes down to -100. All the remaining water vapor, which is a few hundred parts per million in the gas stream, is frozen out onto the surface of the bed material and effectively flushed out of the system. It is recirculated back round to the the cold end of the process and evaporated into the exhaust gases, so we don't have any problem with it. As we go further, the temperature below 100 degrees in the right-hand column, we take the temperature down to minus 125 roughly, and the carbon dioxide is deposited on the slowly moving bed material. It's carried out of the contact region and it's warmed in those lower heating plates on the right to about minus 80 centigrade, where we get carbon dioxide evaporating off, subliming off the granules at atmospheric pressure. So we recover the carbon dioxide as a gas, and then the bed is lifted to the top and recirculated through the cooling plates at the top. So we have a refrigeration system that provides the cold at the top to cool the bed and actually rejects heat into the lower section to warm the bed and to drive the carbon dioxide off. So these commercial technology items, unusual as they are, form the basis for our process. The refrigeration is also commercially sensible. It's a conventional enough process. We can either use a mixed refrigerant process, which is vapor compression type refrigeration, or nitrogen cycle, which is a dry gas only cycle. We prefer the nitrogen cycle, reverse Brayton cycle, using nitrogen or air because it's non-flammable and it's non-toxic, whereas unfortunately in the temperature range we're dealing with, the refrigerants tend to either be toxic or to be flammable, or a bit of both. So it's much easier to have a nitrogen cycle. Now, because we reject heat to recover the carbon dioxide, we substantially cut the refrigeration energy duty. So not only do we recover heat through our heat exchangers, but we recover heat through our refrigeration system. So the overall energy consumption is radically reduced. And in this application, because the temperatures are not so low, we can actually use air in our circulating medium. Dry air, I agree, but air does not, the carbon dioxide concentration in dry air doesn't represent a problem, doesn't freeze up. So we don't have any issues of makeup refrigerant. And again, this is an Air Liquide picture. It's a conventional enough nitrogen cycle process. One of the features of the process that we use is that we produce carbon dioxide highly selectively. It's effectively a kind of distillation, our process, which means we get high purity carbon dioxide. Now, liquefying the carbon dioxide after carbon capture conventionally includes quite significant cleaning up. The process on the right is a whole chunk of stuff out of Lindy's catalogue that shows the brown plant is the complexity needed for cleaning up the carbon dioxide. It has absorbers to take the water out, and it has a fractionation column to remove the other contaminating gases. Now, because of the purity of carbon dioxide we produce, we eliminate all that. So we eliminate a bunch of energy consumption and cost. And the technology that remains is widely available and conventional. Now, when you look at the different processes, there are many perspectives we can take, but let's look at the energy consumption first. You can see here that there are similar processes, A3C, amine and membrane, although A3C is significantly lower energy consumption and has access to lower concentrations of carbon dioxide than the competing process. And then we have direct air capture, which lives in a realm of its own at extremely low gas concentrations, carbon dioxide concentrations in the gas, but also a correspondingly higher energy consumption per ton of carbon dioxide removed. So not only does it have a high capital cost, it has a high energy cost. You can see here in the lower group, the membrane process is not so effective at low concentrations of carbon dioxide. It becomes unattractive to process small concentrations and remove them effectively. Amines are reasonably able to go down to a few percent, 3 or 4%, so that large gas turbines can have their exhaust gases washed with amine successfully. A3C can go right down to below 1% and still remove 90% of the carbon dioxide at that level. So it's quite challenging. At the other extreme, membranes are very good at high concentrations. When you want to remove large quantities of carbon dioxide from natural gases from unsuccessful oil fields, then that's the process to go for. Dimensions are another issue for these processes. They're quite different. That amine, because it uses absorber columns, the columns can be up to 30 meters high and many meters in diameter to provide sufficient cross-sectional area for the gases to flow up. And then you have a recovery column stripping the carbon dioxide off the liquid stream, which is a bit smaller. And you have substantial heat exchangers and pumps in the remaining area. So you end up with a moderate footprint, but it's a tall plant and one that has to be built as you go. You can't put that on the back of a truck and deliver it to site. The membrane plant, and this is for a common size plant, 60,000 ton per year representative plant. The membrane plant, you end up with many containers of membrane modules and a series of compressors in a compressor building to run your membrane plant successfully. A3C, by contrast, for a 60,000 ton per year plant, we probably have 2 trains and associated refrigeration systems. And the different thing here is that these are pretty much the size of containers. The separation trains are about 5 meters high, but everything else is the height of a conventional container. So quite compact. Direct air capture is in a league on its own. Here you can see 2 of the 12 blocks, 150 meters long, about 50 meters apart, that you need to capture your 60,000 tons per year of carbon dioxide from the atmosphere. Absolutely enormous. You need those spaces in between to ensure that you're not trying to take carbon dioxide out of the atmosphere twice in a particular stream. But these are not unlike cooling towers, as we saw in the earlier picture, but they're just enormous. Then, with all these processes, there's an integration with your site. How easy is it to actually connect up and put in, add? Because many sites are not built from new, they exist. We have the opportunity to reduce the carbon dioxide, and it has to be done, and we have that plant already. So, energy source. Amine has a large steam demand, as well as a demand for electricity for pumping. And the large steam demand often means, even with power plant, you have to construct more steam raising plant to raise the low grade steam to drive the separation process of amines. Membranes, they have large compressors, so you're electricity driven. And for A3C, we're also electricity driven because we use compressors in our refrigeration system. The health and safety and environmental issues of these processes differ too. That for amines, you've got the hazardous chemicals, you've got high temperatures, and you've got CO2 hazards from gas escape and asphyxiation risks. The membranes, you have high pressures and you have CO2 hazards, but by and large, they're not so bad otherwise. A3C, we have cryogenic temperatures, well, nearly cryogenic temperatures, so we have hazards from contact, although those are very well contained in cold boxes, and we have CO2 hazards of asphyxiation, but again, manageable. The installation on site is obviously another consideration for any of these processes. For amine, because you've got these tall columns, you have a substantial process of site erection of works, and that means projects with a duration that's measured in months to years, and a deal of local work to connect everything up and make them operational. So the costs of erection are substantially higher. Membranes mostly come in their modules, and you have site-run pipework to connect it all together to a series of compressor packages. And A3C is not dissimilar. We have process modules that will be delivered as a piece and interconnected to create the overall system. The final element of our integration with site is what consumables do we have? For amines, we have the amine makeup because of the degradation issue we mentioned before. For membranes, there's not a great deal. It depends on your compressor. If you've got screw compressors, you'll have sealing oil makeup. If you've got any of the membrane technologies, you will have replacement, maybe a program of replacement over 5 to 7 years to replace the membranes. A3C is not without its consumables. The bed, which moves slowly, millimeters per second, it still wears. So over a year, we would expect to grind down some of the bed material. Difficult to estimate. We believe it's less than 10% a year by quite a margin. So where have we got to? This is an interesting thing for us. Little story. We started out with early development in 2016-17. We applied for patents and we launched a feasibility study with academic and industrial partners. We were successful in being awarded a doctoral studentship, which we supported, that successfully demonstrated the process at lab scale. And we used process modeling tools to establish the performance of the model and of the technology and begin to work forward. And studies have followed up from that on maritime and land-based applications for customers, including the Department for Transport and some shipping companies. Subsequently, in the last couple of years, we've been designing and building a pilot rig. We had a demonstration day only a couple of months ago. With the rig operating, it takes exhaust gas from a test diesel engine and recovers carbon dioxide, which allowed us to do a lot of testing of process components. We know what we've got to improve now, and qualify the process to get to TRL6, where we have a conceivable development path towards commercial operation. Our next stage, we have a planned module of our prototype of 1.4 normal meters cubed per second, which represents about a 1 megawatt diesel engine. In diesel engine service, it would be about 12 tons per day, but we could also handle conventional exhaust gases from, say, a fired boiler, which would be nearer 36 tons per day capacity. And we're looking then to do industrial trials and qualification for marine use and ultimately to sea trials. Beyond that, we're looking to produce under license. PMW doesn't have ambitions to be a manufacturer. We look to use our modular concept from the prototype to produce multi-module applications without having to do scale-up risk. And that would allow us to go up to about 300 tons per day carbon dioxide without changing our design. And the serial module production drives down capital cost, and processing performance improvements will result from learning of the project. So we have an ambitious program here. We're looking ahead. We're keen to grow and develop. We've discussions going on with a variety of interested industrial and maritime investors, and we're hoping to progress this technology and grow our staff and expert base to make this all happen. So thank you very much for listening. I'll be interested to hear your questions. Thank you.
Thank you, Paul. That was very insightful. I would like to give 2 minutes just to see if anyone would like to post questions on the chat. While we are waiting, oh, sorry.
I can post one in the chat. Can I ask one verbally, or do you prefer?
Yeah, sure.
Excellent. Okay. Thank you very much for that. That was very interesting. I've not come across the A3C process before. You mentioned the Mersey side and the northeast clusters there. Are PMW involved in any of those pilot projects, or have you used to kind of get involved in this latest CCUS resurgence we're seeing in the UK?
The projects are slightly ahead of us in terms of our technical offering, so we're not in a position to compete for the projects that are currently in hand. We're looking forward to participating in later phases as those projects progress.
Fantastic. And one further one, I guess. The uptime of this system, is it a continuous system? It doesn't operate in batch mode. How
No,
often
it's
those
definitely
the
continuous,
consumable
yeah.
parts sort of changed out, or is this once this is up and running, this is kind of a self-sustaining system with very little maintenance required?
The process is continuous, and the makeup of bed material, for example, can be done continuously or intermittently without interfering with operation of the process. Obviously, your refrigeration system has turbo machinery in it. Turbo machinery obviously has a program schedule of maintenance. People like Air Liquide build these things and effectively say you can run them for 5 years and then we do a service. So continuous operation with very little interruption for maintenance is what we'd hope to achieve.
Fantastic. Thank you very much. It sounds like a very interesting technology, and already at TRL 6. Hopefully there's a bright future ahead. Thank you.
Thank you very much.
So, Paul, I had a question. In terms of you have mentioned, in terms of size, footprint, and energy requirement, comparison with the existing technologies such as Amine and Membrane. If we have to compare this with the Amine, would there be any indication cost-wise how different things will turn out? I appreciate that you can't give me numbers because cost is very specific to each project. But what would be different if you were about to present a case for your technology, PMW, in comparison to Amine?
Right. I think the significant thing for costs is that because the process is compact, we're able to build the separation module and similar parts as factory modules and deliver the whole thing to site, and have the thing constructed pretty much in factory in a serial production rather than as a one-off custom design that is then erected on site with substantial site labour. That means that we drive the cost down and have faster turnaround for orders, that we have a standard product. One of the virtues of the refrigeration system, for example, is that the single system can be adjusted for different operating conditions, different carbon dioxide concentrations, with little impact on performance and no impact on cost. So the potential for delivering a system without a long feed study process to match the process to the exhaust gases, we can do that quickly and easily. So that from those point of view, the process is easier to deliver. In terms of the equipment, we're not dealing with chemically aggressive conditions through the process. So while we have to respect low temperatures, we don't have to have complex materials for corrosion resistance. So again, we're able to minimize costs reasonably from that perspective, with simpler things to make.
So one point that also does come into my mind and is also one on add-on benefit is that unlike Amine-based technology, the environmental permit issue might not be that cumbersome. Will that be right to conclude?
Yes,
Okay.
indeed. The fact that we're not handling hazardous materials has two effects. One is that the process is simpler. We don't have to worry about special drains for contaminated liquids. We don't have to have special facilities to detect leakages and escapes of toxic material. But also, we don't have to have more complicated site operating practices that may well require different qualifications of staff. So this is in a sense a mechanical process. It's probably no more complex than a refrigeration system so far as a user is concerned. So many industries that don't have chemical processes currently will avoid having to employ specialist staff with chemical expertise to run this process. So there are cost savings in that direction as well as simplifications.
Thank you. I would now like to raise question mentioned by James Lemon, and he's very complimentary of your presentation, and he has asked, he has noticed in one of your slides that you briefly give an idea about energy requirements of A3C process. However, he feels getting down to 150 Kelvin is a small task. How are you having cost-effective cooling method? How are your cost-effective your cooling methods? So refrigeration.
Right, the refrigeration is part of the process, and making that cost effective and efficient is clearly an important part of the work that we've done. But we've also got effectively the cooling process upstream of that, which is regenerative. We call it the cooler dryer stage, where we take gases at approximately freezing point and take them down to -100. And most of that work is driven entirely by recovered cold from the lower stage. And we have a highly efficient heat transfer in that particular heat exchanger that means that we don't have to drive cold down there. We are simply using energy we've already used.
Thank you. I assume that James is satisfied with the answer, as we will see if he comes back. Next question is from Felix, and he is interested in knowing that what is the energy efficiency? For example, what proportion of large diesel engine output would be required to extract CO2? It would then need to be injected into repository as with all other technologies.
Yeah, the capture penalty, if you will, for our process is in the region of 10% of the output of a diesel engine. So compared with the other processes where onboard marine capture, for example, the energy penalty for the Amine process has been calculated by a number of people on different occasions, and they've come out with a figure of between 45 and 55% energy penalty for reduction of 90% of the emissions using the Amine process, and ours is in the region of 10%. So it's getting to the stage of I won't say it's a no-brainer. It's dramatically less painful to implement carbon capture than it used to be.
I think, yeah, Felix resonates with your thought, and he says that 10% sounds very good. It brings me to my question that I can see that, I can visualize that it is a modular design. But for example, Paul, if you would have to, commission your technology to a power plant, let's say 400, 500 megawatt, will that mean that from the flue gas exit, the duct, there will be small modules installed in a cascade way, or will that be a one big house where the cryogenic will happen?
Right. That at that scale, we haven't got a standard design, and
I'm sorry, your voice is a bit patchy. We missed it.
I'm sorry. Our process at the moment is aiming at smaller scales than a large power station, but indeed we could have a large power station serviced by multiple modules. It's cumbersome, that's what we say, at that scale. So our process, as I said in the presentation, for power plant, things like the Amine process have the virtue of being able to be scaled up to very large dimensions. Although there are issues there, our process has yet to grow that far. We haven't got the engineering in place to make it happen.
Thank you.
So at the moment, we're looking at perhaps a quarter of a million higher being the upper end of the scale we would consider confident to deal with.
Thank you. Actually, your line was a bit patchy. I was able to catch main words and I was able to do fill in the blanks. So I'm hoping
Oh dear,
others were
I'm
also
sorry.
too. Others too. I think on that note, I don't see any new questions. So I believe it will be safe to say that David, would you like to do a thanking note now?
Thank you.
Now you are on mute, David. Oh no, we can't hear you, David.
Can you
Sorry.
hear me now?
Yeah, we can.
Yeah, right. I'll start again. I don't know. Right. Okay. Thank you very much for delivering a very interesting lecture. I found it educational, and I was very interested in the comparison of the different methods that you referred to of capturing carbon. And from my understanding of what you have said, it would appear that your method is by far the less costly of all the other methods. And if you are successful, as you hope to be, and as I hope you will be, then I think you might be on a winner that could be very commercially viable in the power industry in particular. And that would be a great thing. I like your comments about the quenching process and the wash gas cooling, etc., and the fact that you prefer the nitrogen cycle to reduce energy consumption. I'm not quite sure how that works, but nonetheless, it sounds very interesting. So, all in all, I think it was an extremely good lecture, very educational, and it was exactly what we wanted in terms of the knowledge of carbon capture and storage. So thank you very much for that. We would normally thank you with a show of hands, and I usually suggest that we do so, even though you can't see it. So thank you very much for that. Okay.
Thank you very much indeed. I
That's right.
appreciate
And,
that. Thank you. Thank you,
we-
David.
yeah.
We can do virtual clapping.
Sorry?
We can do virtual clapping.
All right.
So
We will be sending you a little gift as in a way of thank you. And the gift is a working model of a Stirling engine. You will find it quite fascinating, and I'm sure your family
Wow,
and everyone
gosh.
who sees it will be fascinated by it. So thank you very much for that.
Thank you very much.
Okay. Have you anything
Thank you
else
very
you'd like to
much
say
indeed,
just
David.
before we
Been a
come to
pleasure.
the end? Is there anything else you'd like to say
No,
before we
it's
come? Yep. Everything okay?
Thank
Right.
you very much.
Okay, well, I think that just about does bring us to the end of the session. Our next lecture is a face-to-face lecture, and it's at the University of Salford, and it's on the autonomous vehicle. That's a vehicle that has been developed at Salford that is capable of driving around the campus without a driver. So please come along. It should be very interesting, and it'll be nice to see all your faces again. So thank you very much for attending this lecture, and have a safe journey home. Thank you. Bye.
thank you.
Thank you.
Thank you.
Thank you.